Close your eyes and imagine the universe is perfectly silent. A cold, empty void where nothing moves and nothing speaks. But what if I told you that's a lie? What if the very fabric of reality is actually vibrating, humming, and singing a low-frequency song that we've only just begun to hear? We aren't just living in a vacuum. We are living inside a cosmic symphony that has been playing since the dawn of time. Welcome to Sci Nova. Today, we are diving into one of the most profound discoveries in modern astrophysics: the detection of the gravitational wave background. For decades, we thought we were listening for isolated events, single, violent collisions. But recent evidence suggests something much more grand. There is a stochastic background, a constant overlapping roar of gravitational energy that permeates every inch of the cosmos. To understand this, we have to go back to 2015. That was the year everything changed. For the first time in human history, we actually detected gravitational waves using LIGO. We weren't just looking at light anymore. We were feeling the ripples in space-time itself. It was like being blind for thousands of years and suddenly someone turned on the lights. But even LIGO's detection was just the beginning of a much larger story. LIGO is incredible, but it's like listening to a single drumbeat in a crowded stadium. It catches the high-frequency chirps of stellar-mass black holes colliding. But what about the giants? What about the supermassive black holes, millions of times heavier than our sun, dancing in the centers of distant galaxies? Those collisions create waves, so massive and so slow that LIGO simply cannot hear them. They operate on a completely different scale. To catch these slow, heavy ripples, we needed a different kind of detector. We didn't need more lasers on Earth. We needed the universe itself to act as our laboratory. Enter the Pulsar Timing Array, or PTA. This isn't a machine built in a factory. It is a cosmic network of the most precise clocks in existence. We are talking about millisecond pulsars, dead stars that spin hundreds of times per second with terrifyingly perfect regularity. Think of these pulsars as the universe's ultimate metronomes. They send out pulses of radio waves with such precision that we can track them across the galaxy. By monitoring ensembles of these pulsars over many years, astronomers can look for tiny, correlated timing residuals. If a gravitational wave passes between us and the pulsar, it actually stretches and squeezes the space the radio signal travels through. This causes the pulse to arrive slightly early or slightly late. This is where it gets mind-bending. We aren't just looking for one single event. By analyzing how all these pulsars across the sky fluctuate in a correlated way, we can detect the nanohertz frequency range. These are incredibly long waves, with periods measured in years or even decades. We are essentially using the entire galaxy as a giant gravitational wave antenna, waiting for the fabric of space to ripple in a specific rhythmic way. And the results are finally coming in. Recent data from Pulsar Timing Arrays worldwide has provided what scientists call strong evidence for the detection of a stochastic gravitational wave background. We are seeing evidence at the level of 2 sigma to 4 sigma. In the world of physics, that is a huge deal. It suggests that the signal we are seeing isn't just random noise or a mistake. It is a real physical phenomenon that is actually there. So what is actually making this noise? If it's not one single event, what is it? The leading theory is that this hum is the collective sound of countless pairs of supermassive black holes orbiting each other. Imagine millions of these behemoths, swirling around one another in a slow, cosmic waltz, constantly shedding energy in the form of gravitational waves. They are so numerous and so widespread that their individual signals blend together into a single, continuous background hum. This discovery marks the beginning of a new era, the era of light-year wavelength astronomy. While LIGO looks at the tiny, violent snaps of space-time, pulsar timing arrays allow us to see the massive, slow-moving tides of the universe. It's the difference between hearing a single firecracker and hearing the constant low roar of a distant ocean. We are finally learning to listen to the deep bass of the cosmos. But why does this matter to us? Why spend decades monitoring stars just to hear a hum? Because these waves carry information about the most extreme environments in existence. They tell us about how galaxies grow, how black holes evolve, and how the structure of the universe was shaped over billions of years. By studying this background noise, we are essentially reading the history books of the universe written in the language of gravity. The implications are staggering. If we can map this background, we might even find traces of the Big Bang itself. Some theories suggest that a portion of this gravitational background could be primordial, ripples created in the very first fractions of a second after the universe began. We might be listening to the literal echo of creation, a sound that has been traveling through space for 13.8 billion years just to reach our detectors. Of course, we are still in the early days. The evidence is strong, but we need more data, more pulsars, and even more precise timing to truly understand the texture of this cosmic hum. We are like early explorers listening to the wind, trying to figure out if it's a breeze or a hurricane. But one thing is certain, the silence of the universe has been broken, and we are finally listening. The universe is a lot noisier than we ever imagined. From the tiny chirps of colliding stars to the deep, heavy hum of supermassive giants, space-time is constantly in motion. We are just beginning to tune our ears to the right frequency. If you found this journey through the cosmos fascinating, make sure to hit that subscribe button and join us here at SciNova. There is so much more left to hear. Thanks for watching.